Hello chemists, this is Ms. Placino and you are watching Screencast 1.1 on properties and changes. By the end of this lesson, you should be able to look at different properties and changes and classify them as either being chemical or physical. Let's take a look at the do now. Pennies consist of zinc plated with a very thin layer of copper. So if you were to cut open a penny, this is what you'd see. You've got that brownish red metal on the outside, that is your copper. You can see it's a very, very thin layer. And in the middle, you have this shiny kind of silver colored metal, and that is zinc. So let's say you take 10 of these pennies, you melt them, you stir them or mix them together, and you allow them to cool. Does this represent a chemical or a physical change? Explain your answer. In class, we had a pretty good discussion about this. A number of you said that this is a physical change because melting is a phase change, and phase changes are physical. Stirring them together, well, that's just mixing the components. That sounds like a physical change. And if you allow the mixture to cool, eventually get to the point where it turns into a solid or it freezes. And since freezing is a phase change, that is also a physical change. Other students made the argument that this is a chemical change because when you mix zinc and copper together, you can make brass. And since brass is a different substance, this whole process that we just went through must be a chemical change. So we've got two pretty compelling arguments on both sides of the coin, no pun intended, but the real question is who is right? Is this a chemical or a physical change and why? And really to get to the bottom of that, you have to think about what the pennies look like both before and after this change on the atomic level. So if we take a look at that penny again, and you can imagine where the zinc and the copper atoms are, you'd have your zinc atoms all clustered together in the middle, and then you'd have a thin layer of copper atoms around them. After you heat them and mix them together, you will form brass. Brass is an alloy. Metals tend not to bond with one another, but you can melt them and mix them together. So in that little atomic view of brass, the yellow atoms represent copper, the gray atoms represent zinc, and they are just mixed together in a very homogeneous fashion. They're not actually bonded together, they're not interacting with one another. It's just that you've rearranged the atoms. So in the penny, where it's very heterogeneous and the copper and the zinc atoms are in two very distinct places, in brass we've mixed everything together and we've made it homogeneous. So this turns out to be a physical change, a more complicated physical change than most of the ones that we'll see, but still a physical change nonetheless. Let's get into some other examples of chemical and physical changes. In class, we did a demonstration where we did things like light a piece of paper on fire, dissolve sugar in water, tear a piece of paper into smaller pieces. We formed a yellow precipitate, that's that solid that's being formed by mixing two aqueous solutions together. We boiled water, and we lit magnesium on fire. So you saw these demonstrations and you were asked to classify them as either chemical or physical. So we can just quickly do that now. It turns out that our physical changes are the demonstrations that are really not all that exciting. Tearing a piece of paper, boiling water, and adding sugar to water don't do anything to really change the properties of the initial starting material. Paper is still paper, even if you rip it into smaller pieces. Water is still water, whether it's existing as a liquid or as a gas. And sugar and water can very easily be separated just simply by evaporating the water. On the other hand, we've got our chemical changes, which tend to be more exciting demos. In these cases, the making of the precipitate and the two reactions involving fire, we're taking the starting material and we're turning it into something different by the end of the reaction. For example, magnesium is kind of a grayish colored solid. If we react it with oxygen, which is colorless in the atmosphere, we end up producing magnesium oxide, which is this powdery white solid. So we've got a set of properties that are very different in magnesium oxide than from either of the original starting materials. So let's talk a little bit more about chemical and physical changes. All right, we'll start with physical changes. Physical changes are any sort of change that a substance can undergo that does not alter the identity of that substance. Very important. The chemical makeup, the chemical identity of the substance does not change. So let's look at a real world example. Let's say you have a popsicle. Popsicle is mostly water, sugar, and then artificial flavors and artificial colors. As a solid, the molecules are in a pretty rigid organization, highly organized. If you leave it out, eventually the popsicle is going to melt. The sugar, the water, the artificial colors and artificial flavors are still the same, except now they've got more freedom to move and the arrangement has become more disorganized. So again, the molecules themselves are exactly the same, just their relationship, their order, or their arrangement has changed. It turns out that anytime you have a phase change, it's going to be classified as a physical change. I'd like to take just a minute or so and hopefully review some phase changes. So if we look at a solid turning into a liquid, we know that's called melting. We can do the opposite of that. A liquid turning back into a solid is freezing. If we take a liquid and we continue to heat it up, either through evaporation or boiling or vaporization, you can get to the gas phase. And if you take the gas and you return it to the liquid phase, that is condensation. When a solid goes directly to a gas without first becoming a liquid, we call that sublimation. Something like dry ice, which is frozen carbon dioxide, sublimes. The reason they call it dry ice is because it's never a liquid. It just turns into a gas directly from the solid phase. And the opposite of sublimation is deposition. A good example of deposition is in the wintertime when there's water vapor in the air, and it touches something cold like a windshield or grass, and frost is deposited immediately. It does not first turn into liquid. We got kind of this weird looking picture up at the top. This is our fourth phase of matter. Plasma. We won't be discussing plasma too much in this class. It's kind of more of an advanced topic, but it's worth talking about for a little while. If you take gas and you ionize it, in other words, turn it into its positive and negative particles, you will produce plasma. And this happens like when lightning strikes. The oxygen and nitrogen molecules in the immediate vicinity of the lightning will ionize. This is a very short-lived state in that case. Eventually, those positive and negative particles are going to join together, recombination occurs, and it will reform the gas. And as we go from a solid to a liquid to a gas, and ultimately to plasma, we see the energy of the system continuing to increase. So let's compare our physical changes to our chemical changes. A chemical change does alter the identity of a substance. So the materials that are entering the change are fundamentally different from the materials you get at the end of the change. For example, if you take something and you light it on fire, the material that you started with and the materials you end up with at the end of the reaction are going to be dramatically different. Another name for a chemical change is a chemical reaction. We're going to spend really the bulk of this semester and next semester talking about chemical reactions and chemical changes. So in chemistry, it's really useful to use particle diagrams. And all a particle diagram is a picture of what the substance looks like on the molecular level. So I want you to imagine that you can shrink yourself down so small that you can see the individual atoms and molecules that make up a substance. In the box on the left, we have water molecules. They kind of look like little Mickey Mouses. The two ears, the little white atoms, those are hydrogens. The red atom, the head, that is oxygen. And we've got a pretty organized system in this case. The little triangle over the reaction arrow means heat. So you probably know what happens from experience. If you take something like liquid water and you heat it up, you're going to get the molecules to move farther apart from one another. It's still fundamentally the same exact molecule. It's still water, except initially maybe it was a liquid. And now with that extra energy added, it's turned into a gas. But the molecules themselves have not changed, only the arrangement of the molecules. So again, just to really repeat that and hopefully drive it home, the identity of the substance remains the same. It's still water in both cases. It's still H2O, but the arrangement of the molecules have changed. So now instead of being tightly packed the way they would be in a liquid, we're going to see more space between the molecules, more freedom to move around, more disorganization as we become a gas. Let's compare that to a chemical change. We'll take our H2O molecules again. Try to write a little bit more neatly this time. And this time, instead of heating it up, we are going to pass an electrical current through it. Something you definitely should not try at home, but we'll be doing it next semester in the lab with a safer setup. This is called electrolysis, and our water molecules undergo a chemical change in this case. And instead of just seeing the molecules move further away from each other, closer together, we actually produce brand new substances. We produce H2 gas, so hydrogen, and we're going to produce O2 gas, or oxygen. And later this semester, we'll worry about trying to balance this equation. But for today, the key fact here is that you have got brand new substances being created. So you initially start with H2O, water molecules. You undergo a chemical change, and you produce hydrogen gas and oxygen gas. You can see from the pictures that those are two very different materials as you move from starting to products, so from your reactants to your product side. So I want to switch gears and I want to look at a couple of practice problems. If you haven't tried any of these problems yet, why don't you pause the video for a minute and see if you can take care of questions 1 through 5. What I'd like you to do is read the change and classify it as P for physical or C for chemical. All right, assuming that you've had a chance to do that, I'm going to go through it. We're talking about in question 1, melting copper. We know that melting is a phase change, and all phase changes are classified as physical changes. Burning is a reaction with oxygen. You burn something like sugar, and maybe you have had this happen to you before, you kind of end up with this like black, charred looking stuff. Burning is a chemical change. We're going to make something that is no longer sugar. The word tarnishing. Maybe you've seen silver tarnish before. It kind of gets that weird layer of gray on top of it. Things like tarnishing, rusting, corroding, they're all suggesting that a chemical change is occurring. In all these cases, the metal is reacting with oxygen in the atmosphere. Mothballs sublime. Sublimation is another phase change. Phase changes are always classified as physical changes. Mothballs, I notice we don't use them too much anymore, but they are really kind of nasty smelling little white solids that go from the solid phase to the gas phase without becoming a liquid. They're an organic compound called naphthalene. And finally, number 5, HF reacts with glass. HF is hydrogen fluoride, and hydrogen fluoride can be a really nasty chemical. Hopefully it's kind of a giveaway here, the word reacts. So we know that we're going to see a chemical change. The remaining questions you can try on your own for practice. Remember, if you're interested in looking at the answers, and I would highly suggest that you check your work, you can always look at the bottom of the Unit 1 webpage. So just to finish things up, I'd like you to write a quick 60-second summary of the unit, or I should say of the lesson. All I really want you to do is look over your notes and pick out the key pieces of information. Imagine that you've got a friend who missed class, you see them in the hallway, and they ask you, hey, what did I miss? What did we go over? And you only have 60 seconds to tell them the key pieces of information. Try to keep things to maybe 2 to 3 sentences max, and really focus on summarizing the lesson from today. All right, so that basically wraps up Screencast 1.1 on properties and changes. Hopefully by now you are able to look at different changes that take place and you can determine whether they are chemical or physical.